For years, scientists have tried various methods of arranging the elements, grouping the elements into some meaningful form that could be useful not just for explaining behaviors of elements, but also being able to use them as a predictive tool. And one of these early methods was pioneered by the German chemist Johann Dobereiner in the early 19th century. Dobereiner noted that there seemed to be small groups of elements, usually 3 elements to a group, that shared similar properties. And examples of these groups of 3, one was known as the coinage metals, and these were gold, silver, and copper, aptly named because they are often used for currency. The alkali metals, the word alkali coming from an Arabic word referring to the burnt ashes of a particular plant root, and that's where a lot of our alkali or basic substances come from. These refer to the metals lithium, sodium, and potassium. The halogens were another triad, and the halogens are a group of nonmetallic elements which included chlorine, bromine, and iodine. And when we look at our modern periodic table, we see that there is in fact a grouping of these particular elements. But our modern periodic table is much more than just groups of 3. Another effort to put some order to all of the elements that were known was done by a British chemist by the name of John Newlands, and this was in the mid-19th century. Newlands noted that if the elements were listed in order of increasing atomic mass, that is, from lighter to heavier elements, that every 8th element there seemed to be a repetition of chemical and physical properties. And so hence this became known as the Law of Octaves, and in listing the elements from lightest to heaviest, every 8th element had this repetition. And so this way, the periodic table, if you will, at this point started to take a tabular appearance to it, because now each time you had a repeated element, that began a new row. So elements with similar properties started to line up vertically. And so again, in the 19th century, we're talking mid to late 19th century now, Dmitri Mendeleev, a Russian chemist, proposed that element properties are a direct function of their atomic masses. That is, as they go from lighter to heavier, you will see a progression of these properties as well as a repetition of them. And so he put his elements in periods or rows like Newlands had. However, not all of Mendeleev's rows were 7 elements wide. Right? The first 2 periods, or the first 2 rows, were 7 elements wide. The 8th element started the next row. But his second 2 periods, so rows 3 and 4, were actually 17 elements wide. And that shows some similarity to our modern periodic table with that valley in the center section between the main group elements. One of the important lessons that we can take away from Mendeleev's work is that perseverance pays off. At the time, both Mendeleev in Russia and a German chemist, Lothar Meyer, came up with similar configurations, similar means of arranging the elements, and had similar periodic tables, and they worked completely independent of one another. As they made their tables, they noted that there were some areas where there seemed to be some missing information, some missing elements. And so they had these blank spots. The periodic table almost resembled Swiss cheese. What Mendeleev did, besides publishing his work before Meyer did, and hence getting credit for it, Mendeleev made predictions about those missing elements. He recognized that there seemed to be a pattern set up that elements that fell into the same column shared properties. And so by looking at the other elements that were in the same column as these missing elements, he was able to make predictions. And lo and behold, after he published these predictions, about 2 decades later, some of these elements were indeed discovered, and their actual properties were amazingly similar to the predictions that he had made 2 decades prior. And so this is really the reason why Mendeleev gets most of the credit and why he is generally labeled as the father of the modern periodic table. So if we take a look at the one of the predictions that he made for the element that sits below silicon, the modern day element germanium. At the time Mendeleev put his periodic table together, this was an unknown element, so he named it ecosilicon because it came after silicon. He predicted its mass would be have a mass of 72, it would have a relatively high melting point and a density of 5.5 grams per cubic centimeter. Appearance-wise, he predicted that it would be dark gray in appearance and that when it reacted with oxygen, it would react in a 1:2 ratio, and he even went so far as to predict the density of this compound, which he thought would be 4.7 grams per cubic centimeter. About 2 decades later, when germanium was discovered and characterized, its atomic mass was measured to be 72.61 atomic mass units, melting point of 945 degrees Celsius. Its density was a little bit lower than his prediction, but not far off, 5.323 grams per cubic centimeter. It indeed was a gray metal, and it did react with oxygen to form germanium oxide, and its density was measured to be 4.70 grams per cubic centimeter. So imagine yourself being a scientist or a chemist in this time period, and you're looking at this journal article that's dated 20 years old, and you're comparing the hypothetical data with the actual data that maybe you just came up with in the laboratory, and you were one of the first ones to characterize this element. All right, seeing that correlation there gave Mendeleev's work a lot more credibility and validity. So this led to the periodic law, and the periodic law was a statement that described how the elements properties, what they were determined by. The periodic law stated that properties of elements are a periodic, that is a repeating, function of their atomic masses. And unfortunately, there were a couple of glitches. There were some places on the periodic table that when elements were listed from lightest to heaviest, they didn't quite match the properties of the elements that were above and below them. On the other hand, their neighbor had the same problem, and so it was as if those two elements had been switched, and this was found with tellurium and iodine, cobalt and nickel, and probably most notably argon and potassium. Argon being a very stable colorless, odorless gas, potassium being an extremely reactive silvery metal. If they were lined up in order of increasing mass, they were clearly in the wrong families. And so Mendeleev put them in the proper families and attributed this difference, this glitch, to inaccurate masses. And so the idea was that as time went by and improvements were made to the technology for measuring masses, these problems would fix themselves. Unfortunately, that was not the case. And it wasn't until the early 20th century, when subatomic particles were being discovered and investigated, that Henry Moseley suggested that each element having its own unique number of protons, perhaps the element should be lined up in order not from lightest to heaviest, but by the order of how many protons they have. And lo and behold, when this change was made, it was a slight change, because for the most part, as the elements get heavier, the number of protons increases. But most notably, where it made a huge difference was in those groups of elements, those pairs of elements that seemed to be switched. Every single instance of those, they righted themselves. And so when listed in order by atomic number rather than atomic mass, the properties of those elements matched as they should have, as predicted originally by Mendeleev. So the modern periodic law is exactly the same as Mendeleev's periodic law, except for the very last part. Properties of elements are a periodic function of their atomic numbers. Another way that we can classify elements is whether they are metals, nonmetals, or metalloids. The metallic elements are found on the left side of the periodic table and the center, and by far they make up the majority of the elements on the periodic table. Most of these elements are naturally occurring on our periodic table in the classroom. These are the ones that are shaded in solid black. Some of the metals are artificial, that is, that they need to be created in a laboratory, and on our periodic table in the classroom these are filled in with white. Properties shared by most of these metals is that they are shiny, they are lustrous, they are malleable, they can be formed into different shapes and flattened out, they are ductile, they can be stretched out into thin wires, and they're good conductors, both of heat and electricity. Your nonmetals are typically found on the right side of the periodic table, and the dividing line between these is the metalloids, which is the third group that we'll talk about here. On some periodic tables you will see a stair-step line starting with element number 5, boron, and it steps down and to the right. And so the nonmetals are the elements that are located entirely on the right side of the stair-step line. Overall, the nonmetals show a variety of properties in terms of state. The elements on our periodic table in the classroom listed in black are solids at room temperature, and so you see some of those nonmetallic elements are indeed solids at room temperature and room pressure. Elements listed in red are gases at room temperature and pressure, and we have several nonmetals that are indeed gaseous under normal conditions. And the elements listed in blue, and there's only 2 on the entire periodic table, one's a metal, one's a nonmetal, these elements are liquids at room temperature. And so the nonmetals have the distinction that they have all 3 states in this classification. Overall, the nonmetals themselves, if they're in the solid state, are relatively dull in appearance, very brittle. If you hammer on them, they won't flatten, they'll just fracture, and they're poor conductors, which makes them good insulators. Elements that directly border that stair-step line, dividing line between the metals and the nonmetals, these are referred to as metalloids, and as you might expect, their properties are somewhat like that of metals and somewhat nonmetallic in nature. The one exception would be element 13, which sits directly below boron and below the stair-step line, and this is aluminum. Aluminum is most definitively a metal in terms of its properties. It's lustrous, it's malleable, it's a good conductor of heat and electricity, and so that is the one exception to the placement rule of the metalloids. It does border the stair-step line, but it is not considered a metalloid. And metalloids, as we'll discuss in a future lesson, one of their distinguishing properties is semiconductivity. They are worse conductors than metals, but they are better conductors than nonmetals, and so it's possible to, in certain ways, control the conductivity of these particular elements, and that has very real application and importance, especially in this modern day and age of shrinking computers and cell phones and other electronics.